Now it's on. Whoa. Whoa. Oh my God. These speakers, dude, I'm like an announcer, you know, like these little principal's office. Oh my gosh. That's troubling. Okay. All right. Well, the audio already looks really well balanced on the stream. We're barely entering the yellow range and it's picking up everything I'm saying, so it might just be a little crunchy. Yeah, I guess we'll pull it up and see how it sounds in a second here. No stream?
I don't know if I got the right link.
You just go on our YouTube channel, it should just pull up. Oh, no, you're on it, right?
Yeah.
Oh, but the link isn't coming up or something. The unlisted? Did I mess that up? Just came up in your feed? Alright, yeah, then it's probably good. Do you mind pulling it up, Brody, so we can see how it sounds? Man, this is crunchy, but like in the best way. This is hilarious. What do we sound like?
Oh, I think I missed a W somewhere.
Pretty good. That's it. That audio is pretty good. It's crunchy. It's a little crunchy. I'll turn it down a little bit and maybe it'll undo some of that crunch. Yeah, alright. Oh man. Oh, hype. Alright. Cool. Who just left? That was Jonas. Okay, yeah, we'll probably. Honestly, Jonas is like 13% of the viewers today. I might we might wait a second. So just some. There you go. Is it following? It's following me. That's crazy. All right. So, AI. We said Brody knows it. Okay. All right. Who asked? Man. All right. What if I just turn the room off? Does it still pick up? It still picks up. Room is still on though. What if I turn the room down? Really down? More down? The room's not turning down. That's crazy. All right. Voice in room off. Hey, all right. And then it can still hear me online. That's perfect. Perfect. All right. Very cool. Okay. All right. We should be good now. Welcome back, Jonas. So real quick, a show of hands. Yeah. Okay. It can see me. I'm a little dark, but it can see me. How many of you know about AI? Like, and to what extent? So, like backpropagation. Does that ring a bell? Neurons. Okay. All right. Cool. Jonas, is that? You did. All right. I'm just going to cover like a really introductory like AI stuff today, but I'm also going to talk about the applications in games and sort of the cool stuff that's happening right now. I'll admit it's a shorter presentation today. There's going to be a lot from William at the end where we kind of lead into the next workshop. The next workshop's going to be pretty interesting. We trained AI to play one of the Game Jam games. Or rather, we had gAItor Club train the AI, and gAItor Club's going to give that workshop. So that should be really cool. gAItor as in GAITOR. They're a pretty cool presence on campus. I was around when they were founded. It was like, yeah, good times. Anyways, yeah, Robert, just real quick, your AI knowledge. Do you know like neurons, kind of, maybe? Yeah. Okay. All right. Cool. Well, in that case, yeah, this is going to be. So first, we're going to talk about the applications. So on the applications, why should you care about AI in games? Who recognizes this clip? This is Battlefield 2042. A few seconds before the like famous little Rendazook scene. When I was watching this trailer, I got very excited, and the reason that I got excited is because of the clouds behind the jet. I know that's pretty silly, right? Everyone else was paying attention to the Rendazook, but look at the clouds behind the jet right there. They're actually blowing out of the way. So that's fluid simulation. I'm just going to talk about the different applications of AI in games. We're at a point right now where graphics cards are extremely powerful. And all that we are doing with those graphics cards and the extra power that each generation gives us is higher frame rates, more light bounces. Hey, yeah, more light bounces, higher frame rates. Like it's not, we're running out of things to allocate compute to. So the next big thing to allocate like extra graphics card power to, in my opinion, I think, is fluid simulations. We saw Unreal Engine 5 now ships with a big fluid solver built in for the particle systems. And fluid simulations can be AI accelerated. One of the really cool applications that we're probably going to see in a few years, when a jet flies through smoke, it'll actually carry the smoke behind it. When a grenade blows up in a room, that smoke will actually propagate and blow through the doors, and you'll see little O-rings travel through the room. You know, that would be really, really cool. And I think that's what we're going to see soon with AI. Another big application of AI. Who knows about NVIDIA Remix? Who's heard about this? William's heard about this. All right, so with the latest RTX upgrades from NVIDIA and the release of the 4000 series cards, they created like this whole application that it uses USD files. As game devs, we should know about USD files. We probably don't use them very much right now, but in the next few years, we're going to be using them a lot. They are universal scene descriptions. It's a really, really popular file interchange format right now, and it's becoming more and more powerful and popular. It's becoming like the universal way to transfer 3D models, materials, shaders, scenes, environments, like anything you want with CG scenes. And so what it does is it takes USD files. Well, it hooks into a game that is running on DirectX like 9 or 10, and it rips out all the textures and models and puts them in a USD file, and then it automatically uses AI to upsample the textures, up-res them, and generate normal maps and height maps and stuff. So this is a shot from Morrowind, I think, Skyrim, and you literally just plug in the game, and it goes in, and you can turn all the textures from like 420p to like 8K. And it's really, really cool. It's really powerful. So texture upscaling is one of the big applications we're seeing of AI in games. This is a shot from War Thunder. How many of you maybe play War Thunder? Cool, yeah. So one of my favorite games of all time, honestly. War Thunder recently up-resed all of their old 2K and 1K textures on their vehicles to 8K. They did that by training a neural network in-house. Really cool. So they like ran it through a million like texture files of all their 700 vehicles that they have in the game, and they generated fresh textures. So like this tank used to be really low resolution, and they ran through the AI, and we got like all the scratches and details pulled out without any effort from like an artist or even a technical artist. I guess this role, the person that made this machine learning stuff, falls into the category of technical art. We can also see AI for procedural generation. This is The Legend of Zelda, but some researchers used AI to make a better procedural generator. Procedural generation typically revolves around a very restricted set of rules that we define as programmers to try to create a repeating and reasonable gameplay experience. But with AI, you can leave more to the computer and have the computer optimize around the player's interests. In fact, that's what that game on the left is. It's called, oh man, I'm forgetting, I think Galactic Wars, I think. And what it did was it used AI to observe the player's use of different weapons, of different tools in the game, and it procedurally generated new weapons based on AI models that were remixed based on which ones the player was mostly enjoying. And as a result, you get procedural generation that directly appeals to the interests of the player. They won best paper for machine learning or something in this big competition back in like 2009 or 10, I think. Dude. I want to say Galactic Wars. I'm 90% sure. It's on Steam, and it has really bad reviews because they haven't updated it at all. It's just like they, for some reason, took the free version and made it like $3, and everyone on Steam is angry. But it's a tiny game, but it says a lot about what you can do with AI to actually take, procedural generation, which all of us can probably agree is sometimes really bad. Sometimes it creates these big, empty, boring worlds. And you can use machine learning to identify what the player likes and appeal to them more directly. It's really cool. It's really cool. Some other applications. ML-based games. Does this icon ring a bell to anyone? Back in like But no, maybe? Okay, that's fine. Jonas, yeah, it's... well, no. This is actually, it's just what the game, like, icon looks like. This is a really... this was all over my YouTube feed when I was like 14, 15 years old. Like everyone was playing this, you know, Jacksepticeye, Markiplier, like everyone played this game. This was a fad for a solid like year. And it's a game where you build like these bones, you just create these joints and you give them muscles, and then you literally just define the shape of the neural network for each muscle. You let them evolve over time, and they try to like walk along a course and eventually progress. You're kind of just playing God, and then you let them do their own like mental evolution stuff to actually figure out how to walk and run. But you can create any creature you want, and it figures it out eventually. It was really popular. It was really popular for a long time. It's no longer all that popular, but we can play it a little bit later in the presentation after we're done with William's part if you want to see. It's really interesting. You can see the impact that bigger neural networks have smaller neural networks, but we'll get to what that even is in a second. For now, we're just flexing the different ways that you can apply machine learning to games. There's also machine learning for image generation. So we're going to see this in a second. This is a music video. It's made in Unreal Engine. And I'm going to show you what they did is they just created like an environment with a really basic, ugly character and basic, you know, just environment. They rendered it out. And then they plugged it through an AI like Stable Diffusion. How many of you know what Stable Diffusion is? It's one of those like painting AIs. You give it a prompt, it runs an image. Stable Diffusion and AIs that rely on diffusion as like the underlying method can do not just text to image, they can do image to image, they can do image to video, video to image, text to video. You can generate a whole video from a text prompt. There's even now text to 3D model. You can just type in some text like, I don't know, a penguin eating an apple, and you get a 3D model of a penguin eating an apple. It's not the highest resolution 3D model, but it's really, really impressive. We're seeing some crazy automation there. They're not super accurate 3D models either, but they certainly accelerate creativity. So what this is it's a music video that's been first created in Unreal Engine really basically, and then rendered through image-to-image AI, and you're going to see how interesting that looks. I'm going to skip ahead a bit because the beginning of it, oh, okay, never mind, we skipped ahead in the PowerPoint. Arrow keys didn't do what I expected. So, let me start doing this. I think we can agree it's pretty cool. It's pretty interesting. So it's a very temporally unstable. What that means is that it's not really aware of the previous frame of the animation. And as a result, the environments that it generates and the images that it generates are independent of the previous frame, so you get a lot of stuttering and random effects, but I think we can agree it's vaguely inspiring for the kinds of things you can achieve with AI. The idea here is that with machine learning, we can render entire frames of a game. In fact, that's what NVIDIA is doing now with the DLSS 3.0. We'll talk about that in a second. I mean, this is entirely rendered by it's trippy and it's cool. It's really trippy, but you know, it's structured. It's trippy, but it's structured. Like we see actual shapes here. These can be used to inspire something, but more importantly, they can also be used to, I mean, eventually, maybe like 2 years from now. Yeah. Really chaotic. I'm willing to repeat it and stuff. But like, it's insane. It's really, really cool. But remember, we're in the early days, and the really, really early days of this thing. But we're now really chaotic. Another 2-3 years. Current rate of incredibly potent AI. We can say, you know, a good while unemployed because it's I want to start to do it, but execute the file. I don't think that would work. But it's cool, right? It's cool. It at least gives you an idea of what can be done. This is what it looks like inside of Unreal Engine. You can see that little subway scene that we saw at the beginning. So it's just a normal scene rendered out, pass it through the AI. AI generates that really chaotic imagery based on a prompt and a combination of the previous images. We also see AI for animations. The entire set of animations in The Last of Us 2 are motion capture data. But how that motion capture data is chosen to fill in animation sequences for different actions in the game is handled by a neural network. It's something called learned motion matching that first showed up in a GDC Tech Talk in 2010 by Ubisoft, I believe. And learned motion matching pretty much is just it's a giant AI that picks the best animation frame from a massive library of like millions of frames of mocap data to fill in like every point for where the actor is going to be next. So you place all these like points along the ground. Maybe the points are, they're projected downwards usually. So like if I'm walking forward and it's on the table, it's going to place points on the chair. And then the AI will be like, oh, okay, we're going up. Let me pick, the right set of animation frames to transition to like a knee up on the chair. It's really cool. It's really, really cool. Unreal Engine introduced motion matching in a plugin with the latest version of Unreal Engine 5. It's just now coming out, but it's not learned motion matching, it's just motion matching. So motion matching involves like a very procedural, not machine learning driven algorithm. You can see it's not incredible. It's very like, oh, okay, we're in the air now, let's do the air animation. Oh, we're on the ground, let's do a ground animation. But learned motion matching uses an AI to select better animations from a way bigger library of data. That's the difference. All of those animations in The Last of Us 2 mostly rely on learned motion matching. Text to video diffusion. This is what I was talking about a second ago. So this is pretty cool. This is we've all seen text to image. This is, you put in a prompt and these videos are all generated by AI. The difference here is a quality called temporal stability. They're aware of the previous frames of the animation. Pretty cool. Just, again, wanted to share cool things that are indicative of what we might see in video games. They are. Like, you talk to an NPC and there's a quest line, you can have an image for that. The conversation with the NPC can be machine learning driven. Entire frames of a game's like gameplay can be rendered purely on AI. And that's what NVIDIA is trying to do right now. A golden doodle playing in a park by a lake. Like, look at that. Crazy. Coffee pouring into a cup. You can see it's really trying to figure out what the liquid is supposed to be doing. But it's vaguely convincing. Panda driving a car. A panda drive, yeah, it was like top right. It's one of the prompts that plays on here. But these are really impressive. Water swishing around in a cup, very cool effect. Completely inaccurate, but kind of convincing. Kind of convincing. We got like jelly beans falling into a pattern. It even handles text prompts. So this is by Google. Yep, panda eating bamboo on a rock. Crazy. Wow. Look at that. That even, Jesus, it follows the water droplet and it understands that the water droplet hits the water surface and then creates further splashes. Another splash. Smaller ones create splashes. Insane. Really, really, really cool technology. So these are things that will have an impact on game development. Realistically, like they just will. Rendering acceleration. This is a really cool one. So I'm going down the list of all the ways AI is going to impact game development. I hope it's not too boring. I think this stuff is extremely cool. This is NVIDIA's new DLSS. Who knows what DLSS is? Hopefully we've all heard the marketing terminology. DLSS is, no? Okay, yeah, no, cool. No, that's fine. I'm sorry, I didn't mean to. So DLSS lets you render, DLSS is an upscaling technology from NVIDIA. So what it does is your AI has like these, your GPU, your graphics card has these very like AI specialized processors on them, and those AI specialized processors run a very lightweight neural network that lets your game render at like 480p or something, and then scales it up dynamically to 1080p. And in doing so, it keeps the final image looking very accurate. It keeps the final image looking really, really accurate. The way it does that is by not just scaling up naively, as we saw with like the textures earlier, but it also scales up based on the motion vectors. So every frame that's rendered in the video game, every pixel on the screen has like motion vectors that are computed based on the way the character's moving and what the camera is seeing between now and the last frame. So it takes all these things into account, and it generates a much higher resolution image. So your computer can sweat a lot less generating a low resolution render, and then DLSS scales it up. With the latest version of DLSS, it also predicts an entire frame ahead and inserts it into the render. So now, when you're playing a video game, your CPU is like, okay, let me render a frame, paints the screen, gets you like a 480p image, your graphics card takes it, makes it 1080p or even 4K or something, and then your graphics card, without even requesting for the CPU to talk again, takes that past image, the last couple of images, and paints a new image of what it thinks you're going to see in the next frame, and it looks perfect. It works in any game, and it looks perfect. It's crazy. Deep learned super sampling. So SS is super sampling. You'll see that in a lot of acronyms. So if you've ever in a game's settings gone to like anti-aliasing, like AA, there's a million anti-aliasing algorithms, FXAA, MLAA, SSAA, super sampled anti-aliasing. Deep learned super sampling is, you know, it sort of solves the aliasing problem as well, which is like those jagged surfaces or jagged edges at points of contrast on your screen. The other big thing, this happened like 2 weeks ago, and this is easily the most impactful thing that none of us will ever actually really notice. AI found ways to multiply matrices with fewer multiplications. It is crazy. Like matrix multiplication is typically a very programmatic process. It's like very linear and very nasty. If you want to multiply like a 20 by 20 matrix with another 20 by 20 matrix, there's like a widely accepted set of multiplications and additions that you do to come to the final result. You have to do like, oh, okay, A3 minus A1 times B1 plus B2, and it just works. These are computed from smaller matrices. So we know how to multiply like a 2 by 2 matrix, and by knowing how to multiply a 2 by 2 matrix, you can do 4 of those to multiply an 8 by 8 matrix, or a 4 by 4 matrix rather. It just builds up from the smaller ones. However, we don't know if that's the most efficient way to do it. I believe it was a Google team, TensorLearn, I think, Alpha Tensor, that's what they called it, which I think is part of the same team that did like AlphaGo and DeepMind. They made a game. They made a game where the AI tries to do row substitutions and like just basic linear algebra things to get to a result faster. And it was able to find new ways to reduce the complexity of multiplying 100 cell matrices by 100 cell matrices by like 10-20%. None of us are ever going to like tangibly touch this stuff. It's a discovery that is purely mathematical, but it will literally improve rendering performance and graphics card performance by like 10-15% just magically, because we can now do the math with less steps. Crazy. Do you know how it works? How it improves that, how the AI works? Yeah, it's I can pull up the paper for it. I read it, but I haven't yeah, well, this AI was trained to play a game, and that game involved trying to reach the final correct matrix output, not from, you know, doing the standard like multiplications, but first doing linear algebra operations that like shift the rows on the matrices, move them around to simplify it. And these are steps that like would have required a human like literally billions of guesses. It's just guess and check. We have no good way of doing that. But the AI was able to detect basic patterns, and after like I don't know, 20 billion attempts or something, it found the answers. Like their paper listed some hilarious numbers. It was like in the order of trillions of attempts before it started finding faster ways to compute matrices. It's a huge impact. It's a huge impact because if you know how to multiply a 100 by 100 matrix with another 100 by 100 matrix, you can use that same thing from earlier that I said smaller matrices build up to bigger ones, and now you can do a 2000 by 2000 matrix like 5-10% faster. That's insane. Like everything is matrix multiplications under the hood. Even AI itself involves tons of matrix multiplications. A matrix can also be called a tensor. That's when you hear TensorFlow for like AI libraries. That's what that's referring to. So, anyways, very cool. AI writing, right? Hopefully, in a couple of years, we're going to be talking to an NPC, and the quest line isn't going to be boring. This is something called AI Dungeon, where you have a chatbot with the AI, except that chatbot lets you create any story you want. It lets you play any story you want, and it's very, very aware of what the meanings of your words are. I think it runs off of GPT-3, which is like this big, impressive model. If not, then it runs off like GPT-2 and some in-house adjustments. But it's really cool. You give it a prompt of what the world looks like. Like you literally describe the world. Like I live on a castle in the clouds above like a rainforest village named Erdogan, and it literally accepts that and then gives you a story based on the description you did, and you have text prompts that can drive you like what do you choose to do when you encounter the I don't know, iron golem that you said lives in Erdogan, and it's like, oh okay, I choose to punch it, and it says like, oh, the iron golem dents and it's like shiny metal glistens in the light. Like it's very aware and understanding of what your text prompts mean. That sort of technology will really accelerate like quest line production. I mean, how many RPGs have you played where the quests are like disgusting? There's a lot of really boring. Nothing needs your help. Yeah, exactly. So, and then finally, this is probably the simplest one of all. Hey Siri style commands, right? So. These are two of my favorite flight simulators on the left. This is Arma 3, and that's Phasmophobia. All of these games have something in common, voice commands. So you can talk to your AI teammates and they respond. The teammates aren't driven by machine learning, but the voice commands are, a way of machine learning kind of making its way into games. We might see a lot more of that. Like single player games are probably a lot more exciting if you have like teammates to talk to, because maybe you have no friends. But that's VTOL VR really impressive. You can be like, hey, wingman, orbit, wingman, do this, do that, and it recognizes, like, AWACS, describe this target to me, and it's really cool. It's really powerful. So Phasmophobia has a lot of voice-based gameplay. How many of you have played Phasmophobia before? I'm going off the seat of my pants here. I have no idea what Phasmophobia gameplay is like. I've never played it. I just know that it relies on voice commands a ton and that the ghosts talk to you. Yeah. You have to gather evidence, okay. Spirit box.
And what happens is the idea is that the spirit box can basically have different, and so it tries to pull messages out of it.
I see.
Think about like turning the tune on the radio to different, like making message out of.
Interesting.
Like.
Yeah, sure.
Like that.
Okay.
Use different like.
So it has like a pre-recorded voice message on the voice box, and you like play this mini game to pull out the different words from the pre-recorded message. Okay.
Also generally like.
You say the ghost name. Well, that's so. How is that being done? There's some amount of AI there that's trying to understand what your voice prompt is. I don't know if it uses like an internet API or if it's like a local model that gets downloaded. I know that iPhones for the longest time have been pushing like, oh, we do all your voice processing locally so that the cloud never gets to find out what you're asking for, or never gets to hear your actual voice because privacy, and that's respectable, but So I mean, the point is that if a local model can run on your phone, it can probably run on your computer. So it would make sense that it's like running on your PC. So machine learning in games, very cool. So you can do something on the 3. There's a lot of like voice commands in there that you can do. Oh, and this is perhaps the most complex one by far. Sports games. Oh my God, sports games are insane. You guys play Madden or FIFA or something? I've never played them. I've watched so many videos on them though for like the technical breakdowns. It's crazy. Both FIFA and Madden since FIFA 22 and now Madden 23 use really deep machine learning. It's kind of like learned motion matching. So remember, learned motion matching is like, okay, we have all this mocap data, let's pick the right one for the next frame. It's that on top of learned decision making for like the 5-10 options of what a player is going to do when they hit like an incoming football. And it's all physics driven animation on top of that. So like if there's a football coming in, there's like 10 places that it could be. Motion matching predicts all of the actions that the player could possibly take to reach the different points of contact with the football. Then there's the like defending team and how they're going to interact with them. The entire game is built around the physical interactions of player models. Like that's hard math. That's really intense stuff. So they use a lot of machine learning to pick the right animations, to generate the right animations and interpolate between them. This is a cool thing from a paper that I found that I was reading on machine learning in basketball. They were using they were taking the last like 10 frames of the animation, so like the ball going up and down, your hand going up and down, and they were doing like a Fourier transform on them to find like all the different wavelengths that come together to create the motion, and then they were training a model on the like frequency spectrum, and that's yeah, like these motion phases have to do with that. And yeah, do I understand it all that well? No, I don't. This is stuff that researchers are doing and working really hard on. However, you probably noticed this entire time, we were talking about generative AI. AI that creates things in games, AI that responds to like voice commands. One of the coolest applications of AI is also just adversaries, right? That's the most obvious one. When you play against an opponent in a game, you want that opponent to be interesting. We tend to be really bad at making interesting opponents. Like you play some. For bots. Yeah. No, bots was incredible. Bots was really good, and it's all the chaos in it. But this is a game called Planetary Annihilation. Planetary Annihilation is a real-time strategy game. It's one of my favorite only real-time strategy games, really. And it's one of the things that makes it extremely unique that the player that you're playing against, the AI that you play against, is entirely a machine learning model. It's a machine learning model that has been trained to play against itself. That's a really good way to train these models, is just put them up against each other in like an accelerated world, do it like a million times, and over time they get better at playing against each other. Really cool game, and it makes for really convincing AI that you actually feel proud of that you beat. It makes the AI much less cheesable. You know, they don't walk into a corner or do just idle animation until they see you walk to the last spot that they saw you and then give up. Yeah. This was released in, I think, 2013. 2012 or 2013. It's one of the most impressive applications of like machine learning in games that I've seen. And a fun fact, the developers of it, they were part of a company called Uber Entertainment. Uber Entertainment had terrible publishers. They sucked. The release of the game went really badly because they overpriced it and didn't deliver on a lot of Kickstarter things, but it wasn't the developers' fault. The developers broke off from the company. They started a company called Star Theory. Star Theory was acquired to make Kerbal Space Program 2, and then Star Theory dissolved, and all the developers just joined the new team that's working on Kerbal Space Program. So I love Kerbal Space Program so much. It is like my most played game in terms of hours. And I also love this game because it's so incredibly complex and impressive and beautiful and fun. And it's a cool team. It's a really good team of developers. They're all based out of Seattle, Washington. So yeah, just really cool, really cool. So machine learning, let's get to the education. Jonas, yeah.
Just on that last, are there any games already that guides how gameplay and how the meta is?
I see. Are there games that train their AI based on how players play the game and how the meta changes? So you can use AI to discover the meta by having an AI play your game like a million times and over time finding out how that AI optimizes to break your game. That's really important for like the pre-production of a lot of games that use a lot of economics. Stellaris, for example, or Path of Exile. These games may rely on a system like that. I saw at least 2 papers while I was researching this about using AI to pre-play extremely complex games in order to better understand what the natural meta will be, because the AI tends to find the meta over time. As for AI responding to player input as you play the game, generally that is much less common. So that game that I showed earlier, the Galactic War thing that I think is called Galactic War, and I'm not even sure. Galactic Arms Race. That's it, Galactic Arms Race. So this guy on the right responds to what the player is doing and keeps regenerating fresh neural networks based on that. So it takes like these really simple neural networks, and those neural networks do what? They encode a weapon system in the game. And based on how much the player is using that weapon system and is enjoying it compared to like other weapon systems, it mixes them together to generate new weapon systems. So you keep finding pickups that are more and more interesting to the player. That's like one of the only examples of that I know of. In fact, there's very few games right now that are using machine learning effectively, which maybe speaks a lot for how underserved of a market is. Like there's a lot of potential, but yeah, that's rare. That's relatively rare. I think there's a racing game that does that. I don't know if it's like some Formula 1 game or something, but I know there's at least like one racing game out there that reacts to your ghost players and trains off of them slightly to get better at beating you over time. Like your ghosts, I mean your like, previous runs. I'm not entirely sure. I wasn't able to find anything like that, and I spent a good few hours trying to research some of these applications. But now I'm going to talk about actually like what AI looks like behind the scenes, what it is at the most basic level. So this is a neuron, and if you're not convinced, that's what a neuron looks like. They kind of look the same, right? So that's all the proof you need. Neurons are really, really cool. Neurons in our brains and neurons in neural networks, which are what make up machine learning, not that different. The difference is that our brains fire over time. It takes like a few nanoseconds for a signal to disperse. Most of the simulated neurons in our networks don't take time, but there is such a thing as a temporal neural network that inserts delays and loops, and the field of AI research is really diverse. I think I'm going to raise the screen, maybe. Maybe I'll work over there. Can you guys all like see this area? You think this is okay? Maybe if I go like from here and above. That okay? All right, cool. Yeah, I'll do that. In fact, I'll turn on the light as well. The lights in this room are really confusing, you guys. Like really confusing. Look at that. I don't even. Some of these lights, I think it's like these guys over here are the side lights. Really, really strange lights. They turn on so randomly. There's like a whole like truth table on those like 10 switches that I need to navigate like, what light does what. So all right. So neuron, cool. Hey, great. The camera can see the whiteboard really well. Beautiful. So neurons take a bunch of inputs. Right. Single neuron takes like maybe 3 inputs, let's say. And what does it do? It adds them up, okay? So it weights each one and it adds it up. So it goes, all right, here's input, x1, here's input x2, here's input x3. Chalk is awesome. And it has a weight associated with them. We'll do weight 1, weight 2, weight 3. That's a 3. And it has an output. Or maybe multiple outputs, but it's all going to be the same number that it outputs. It has like a single output that gets distributed to maybe like a million other neurons. I don't know. So what it does is it takes all of these and it adds them up. X1 times W1 plus X2 times W2, X3 times W3. So say X1 is like 0.7 and the weight is 1. This one is 0.1 and the weight is 0.5, and this one is 0 and the weight is 1, so that's 0 plus 0.05 plus 0.7, so we end up with 0.75. And this final number gets plugged into something called an activation function. So that's what all these guys here are. These are all activation functions. So they're literally just functions that map this number to a new number. In our cells, this has to do with like the action potential. So there's all these like calcium ions that flow in and create this like electrical pulse. If enough of them flow in, the neuron lights up and pulses to its neighbors. So in our reality, and it really varies. We don't know that much, I think, about how exactly neurons output, but that could be described as like this function. So any value that's like up to 0.5 will produce no output, and then anything above 0.5 will produce 1. So that would output like 1 if we were using this function that looks like a step function and outputs, 1 at 0.5 and 0 before 0.5. Does that make sense? Activation function. It describes the threshold for the neuron to activate. This is just like an introduction. It's not really going to be pure game dev today, but this is important stuff because we're all going to be engaging with this stuff in another, I think, 5-10 years. No matter what job you end up doing in game dev, whether you're an artist or a musician or a technical artist, a programmer. So then it passes this output to a bunch of other neurons. Maybe we use a different function. One of the most popular ones is called ReLU, R-E-L-U. It's that guy up there, and it outputs like 0 up to a certain point, where then it becomes a linear function to 1. These aren't, picking one of these is a very experimental process. Most neural networks, like the default go-to one is ReLU. Anyways, training a model. So a model is a bunch of these neurons taped together. That's what that is. So you have like a big line of inputs, and those inputs can be, these x1, x2, x3, they seem really abstract here. These can be the values of a pixel. They can be the distance to the nearest wall, or our player's health. They all have to be encoded as 0 to 1 values. So if your player's health is 0 to 70 for some stupid reason, then your neuron should hopefully divide by 70. So you go from 0 to 1. But they all are going to be 0 to 1 values that enter the neural network, and they describe whatever you want, literally whatever you want. You just plug in some random inputs. Maybe it's like our current velocity, our current momentum. That's 3 numbers in a 3D world, another 3 numbers. You can have a really, really big input layer. And then your output layer is, again, just going to be a neuron that's going to encode for some decision. And that decision is going to, hopefully, it's going to be something. It might be like, when this neuron lights up, move upwards. When this neuron is not lit up, go downwards. When this neuron is lit up, go right, go left, shoot the gun, flap your wings, I don't know, whatever you want. But the idea is that you create a neural network that takes inputs and creates outputs that are just going to be these numerical values that mean something. You decide what they mean, you train the neural network based on that. So training, what does training mean? This is the most interesting thing. It's called backpropagation, and it's based on our general understanding of how our own brains and neurons work, and it involves strengthening the connections of neurons that fire together. So what are the connections? They're these like weight values. Over here, you can see all of these like lines represent each neuron's connection to all the other neurons in the layer. So every stack here is called a layer, every like vertical stack that you see. And in the world of like deep learning, there would be, maybe hundreds of layers that are hidden layers, because no one cares what they look like. You just define a number. You're like, okay, let me just generate 100 layers, each 20 tall of neurons, and it would look like that image, but expanded with like literally 100 columns in the middle. Yes, Brian.
So wait, it's like random.
At first, yeah, you get to pick the number. You can be like, I want to create a jellyfish with like two neurons, a planarian, right? Like a really, really like dumb creature. You can do that, or you can generate millions of neurons, and now you'll have a neural network that can do really complex things. You decide how many neurons you want. That's where that's for people who get paid a lot more than we do. It's
You can't just say you can't just say I want millions.
you can. Well, so the trade-off is computational time, foremost, and secondly, wasted neurons. So, in fact, there's entire AI models that do pruning. So they go in and they give your neural network a lobotomy, but they only lobotomize like the neurons that are useless to the end result. So they go in and they're like, oh my god, okay, we ran like 1 million tests, and it looks like these 10 neurons barely even get used in the final output. Let's shave them off. And you eliminate them from the training process, and then the training can go much faster. It's a trade-off. And if you have too many neurons for a really simple task, like say we were trying to predict, Flappy Bird. Let's say it's Flappy Bird, right? And the input is time. The input is time, and the other input is how close we are to the ground. And we want to predict when you're going to flap. Well, I think that's almost trivial, right? Because like if you're really close to the ground, you're going to flap. That needs like 3 neurons or something. Because each one of those neurons is going to encode, like, okay, when I'm really close to the ground, I'll put 1, and it's going to not care about any of the other weights. Like, literally 1 neuron is probably enough to decide from closeness to the ground if I'm going to flap in the next frame. You see what I'm saying? Like, that, all that would take is, like, 1 neuron to figure out, okay, I'm close to the ground, let me flap. If you want more complex things, like I'm close to the ground and I'm close to a pipe, so maybe I should especially flap, or I'm close to the ground but my head is close to the pipe, let's not flap, that would take it would still maybe be a single neuron, because it would give it a negative weight. It would be like, okay, my distance to the top of the pipe is, like here, let's draw a pipe, let's draw the Flappy Bird right here, and another pipe right here. And Flappy Bird's like, oh no, I'm really close to the pipe, but my head is also close to this one. So let's say this value is like 0.2 on the range of how close you can be to the pipe. And this value is also 0.2 on the range of how close you can be to like the surface beneath you. The neuron would have to weigh these things. So you'd be like, okay, 0.2, this guy becomes like 0.2 as the input value. So it's a single neuron, right? And it's your last brain cell playing Flappy Bird. So this single neuron right here would like, it would weigh this. It'd be like, okay, my head is close. I'll weigh this at like 1, and I'm also close to the pipe beneath me, so I will weigh this as like -1. And the weights can be values between 1 and -1. If I think I might be really wrong about that, but if they're not, then it's just like another neuron down the line that inverts the process. And from this, these two would add together to equal 0. So it would be like the neuron would decide to flap based on this comes out to the equation, right? The decision for the neuron to flap is the weighted average. It's the distance from its head to something minus the distance from its like feet to something. That's a vaguely reasonable rule, and over time that neuron would figure it out. Yeah, Alex. Yeah. No, you're good.
Input value, weight them.
Yeah.
Run it through a function. And like it's a weighted.
Yeah.
Then you run it through a function.
Yeah.
So you want to use it, or like that's kind of is that like what you want? That's what you want.
That's what. So I haven't even explained training yet, but yeah, I'm about to get to like what you want versus what you're initially getting.
Because have a whole like what a whole model outputs of one result, I guess, or like do they just share certain neurons?
A whole model outputs a list of neurons. So at the very last layer, there might be like 20 neurons stacked together. And each of those might mean something different. You've decided what that means, and their meaning has been given to them by the function that is created over time through the training process. I'm sorry, I realize we're a little low on time, so I'm gonna like wrap this up. Oh, you don't mind? Okay. Well, I'll be somewhat quick. So, long story short, lots of neurons together. There's a training process here, right? These weights, I decided them just now because I put my big monkey brain to the test and I figured it out. I was like, okay, these seem like a reasonable assumption to make. Like -1 and 1 makes sense. How does a neural network actually figure out those weights? Those weights, when you see, we trained a 13 billion parameter neural network, that means 13 billion weights, 13 billion connections from neuron to neuron. The sole thing that that the neural network solves for is the values of these weights. It can't control the inputs. It produces the outputs by adding together inputs in stacks of neurons, propagating to the next layer, more addition, more averaging, but the only thing it controls is these weights over time. Yes? You can also change the activation function. So we can use the step function. We can use ReLU, which looks like that. You can use the sigmoidal activation function. You can do all sorts of different activation functions. These are called hyperparameters. That's the term for all those different values. They're hyperparameters. They are the parameters that the user controls of the overarching brain. You're designing the brain. You can also control the structure, right? So this is a simple neural network that is always going to be like a bunch of layers together, maybe the output layers, right? It's just, all these different neurons between these different layers. There's different ways to structure this. You can have layers that talk to the previous layer. You can have delays in the neural network. So you can say that this layer is weighted based on this layer's outputs. You can design some crazy neural networks. There's a huge map of the designs of them. There's something called biases. So they're added neurons that float off to the side, and all they do is they add their value to the output. So this is to create certain other features. There's data processing that you can do between the layers. So you can perform a convolution. We're going to get to that in just a second, but the world of designing neural networks is really, really deep. Those are the basic parameters. The activation function, the number of neurons, the number of layers, what are you going to give it as inputs, what are you going to give it as outputs, and the training data that you're going to pump into it to actually figure out these weights over time. But there's a lot of intermediate steps that you can take to create really fancy neurons. Yeah.
At what do you automate having a billion?
Automate.
That's the hardest part about
Automate the inputs. What do you mean? No, sorry.
A billion. Let's say you have a billion frames.
A billion parameter weights are connections between neurons. Yeah. Yes, that's common. Yeah.
it is common that
To answer, I'm not sure if we understand your question, Alex. When the inputs, you decide what the inputs are. So that first layer of neurons is going to be one neuron. We don't even need to call them neurons necessarily, it just makes sense because each one of these neurons is going to be connected to every single neuron in the next layer. This guy's going to be connected to every single neuron in the next layer. These two can be the two input values that you want. I have to decide whatever they are. So if I want my neural network to predict when I'm going to tap the screen next, then I'm going to have nothing but a single output neuron. And it's going to take all the weights of its final thing, and this is going to be the output. It's going to be either like a 1 or a 0 or some in-between value that we, round. And we can decide that the two inputs are going to be like, I don't know, time since last jump. It's going to be a 0 to, that's a difficult value, right? Because that can go up to infinity, but you can pick some realistic values and just divide and give it a range, be like 0 to 1, where 1 codes for 5 seconds and 0 codes for 0 seconds, because in Flappy Bird, in 5 seconds, you hit the ground if you don't flap. So time since last jump, I don't know, height above the ground, time elapsed in the game. Like you can pick whatever you want, and for every different input that you add, it's just another neuron that's going to be connected to every neuron in the first layer. Does that make sense?
So you can have like
You can have 3 inputs and a billion ways. Yeah, you can keep adding like tons and tons of neurons to the first layer, and they all just have to be connected.
Interesting, okay.
Yeah, you add like as many neurons as you want. Just keep, that's, yeah, yes, Brian.
So what
No need whatsoever. In fact, they are a black box. There's no way, like those weights, if you look at them, are just chaos. They're just raw chaos. But the end result is meaningful. You're not going to get anything at all from looking at those weights, in most cases.
I mean, neural networks, it doesn't seem that hard to do.
Well, yeah, making a neural network, in fact, it's literally like 4 lines of code using a TensorFlow. Look, we made a neural network. This is using I think Keras from TensorFlow, popular neural network library. Literally, just our input is going to be 28 by 28 values. So that's going to be how many input neurons we're going to have. It's going to come from an image that's 28 by 28 pixels. The input kit is 28 by 28 pixels. Each one just encodes a single 0 to 1 value of how bright or dark it is. So this could be like literally just an image of like a 1 drawn like this. This is like a really classic neural network problem, and we encode this into 28 by 28 pixels, and it's just like, okay, this one is a 0.1, this one's 0, oh, this one intersects with the 1, so this one's like black, it's lit up. So you take in an image that's going to be a number, and then you do layers. First layer, 256 neurons tall, they're all going to use ReLU. This one, 192 neurons tall, all use ReLU. 128, ReLU. 10, softmax. Softmax is I believe it's the sigmoidal looking one that looks like that. So, and just like that, we've created a neural network, and we've applied these activation functions to every stack of neurons. And this is literally to figure out what number I just put here. So notice how there's 10 outputs. Each of those outputs is going to light up for like 1 through 10. So if I draw a 1 in here, all those 28 by 28 pixels get fed in, and it's going to output, oh, I think I see, if there's 10 output neurons, and they're going to all output a value. So for 1, maybe 0 is like, I don't see any circles. So it goes, I see a value of 0.2 for how much I think it's a 0. For 1, I think it's a value of 0.9 for how bad I think it's a 1. 2, 0.1. Like, it's going to give an output like that. And that's how you know that it's 1, because 1 is the one that was most likely output. Does that make sense? Does that sort of thing? Alex? I still haven't even put backpropagation. We're running out of time, guys. Man, I mean, if you're willing to stay in the meeting, by all means, but William has a whole cool PowerPoint about how he set up a game to do AI. And yes. Oh, I was going to recommend, dude, 3 Blue 1 Brown's video on this stuff is incredible. I was looking at it before I came here today. Yeah. That image is from his. Yeah. 3 Blue 1 Brown, so good. I'm just going to write that up here because, literally the best math channel on YouTube. 3 Blue 1 Brown. His logo is like an iris that's mostly blue and then brown everywhere else. It's awesome. Great YouTube channel. Let's talk about training, because training is it's the key that we're missing here. How the hell do we figure out its weights? And this is a process that seems intimidating. It's not. It's not difficult at all. I'm going to pull up the screen for this to explain training for a second. So I learned this from the 3 Blue 1 Brown video. So I'm just giving you the shortcut here, but in fact, let me try to turn off the projector screen and do that. Yeah. Oh my god. Oh my god. Oh, I didn't know it would be there. I did not do that, guys. That's hilarious. Oh my god. Oh, dude, that's sus. I didn't do that. That's crazy. Okay, backpropagation. Backpropagation. So, the neural networks work. You give them a bunch of data to train them. Making a neural network, making a model. A model is another word for like a neural network. It might combine multiple neural networks together. You might have one neural network that does one thing. The output of it goes into another neural network as part of another thing. There's a lot that you can do with structuring big, complex creations of neural networks. But let's talk about backpropagation. So say we wanted to predict from our Flappy Bird game. I'm going to take a second to draw like Flappy Bird up here. Say we... Flappy Bird would be like an example of reinforcement learning, so that might not be... That would be good. That would be good. Let's say we have a neural network that that encodes for when to jump. And that neural network, over time, takes a stream of inputs. In fact, this is going to line up really closely with what Kyle is going to be doing with our game for the next workshop. So we have a list of inputs. Maybe we have time since last jump. Maybe we have velocity. And velocity is actually, this is actually going to be 2 neurons because they each cover, the x direction and the y direction. So velocity x, velocity y, whatever. Maybe we have distance to nearest surface. So every frame, our little Flappy Bird character is, running a bunch of line traces out, and he's like, oh, this one's the closest one, or this one's the closest one. So Flappy Bird, we've got this neural network. We have a layer. I'm just representing it as a line, right? And this is connected to all the neurons in there, and this is connected to all the neurons in there, and so on and so forth. I'm not going to bother drawing it. The point is, let's say we start this neural network with all of these weights, all of these values completely randomized. 0, 1, negative 1, 0.5, 0.25, negative 37, 69, 0.69, 0 to 1 values. Doesn't matter. You create random weights at the start. And then we play the game. So we play the game, right? Flappy Bird starts, doesn't even flap. It's the ground. There are like 15 neurons here. Maybe there's a bunch of layers here that were all doing their thing. I'm just, being an artist here. There we go. Yep. Cool. So, and then all of these predict for every frame, should I flap? Okay. We run it once. We fail. We're going to train this neural network to see if we did a good job setting up all these random weights, completely randomly generated what the values were for the connections. The main thing that you can do is reinforcement learning. So reinforcement learning says, let's find a value by which we can say how well we did relative to like the previous values. So the bird starts here, and it made it like 5 meters because it flapped once in the start. 5 meters is like our new high score or something. This would represent a cost function. So the higher the cost is, is really like how far behind our top score are we. So if we run this a second time with another set of randomly generated weights, and we managed to only hop like halfway, it would be a loss. We've lost like 2.5 meters of distance or something, because our bird is really dumb. And what you do is you have this like cost that then gets computed for this neuron. So it's like, hey, this final neuron sucked. How far off was it from its target? It was 2.5 away from its target. Okay, so what we're going to do is we're going to say that all of the connections to it that influenced its decision. So say this connection was weighted like positively, this one was weighted 0, this one was weighted like 0.7 or something. Since we have, since we were like a little bit far away from our goal, And our goal was to be like a higher value or something. This isn't the best example. This really isn't the best example. It's a little different with reinforcement learning, so I apologize. A better example would have been like some one-to-one thing. Like this, the predictor network here makes a lot of sense, honestly, to explain this. So let's talk about the predictor network instead of predicting like what am I drawing on the screen? Is it a 1? Is it a 2? Is it a 9? Is it a 0? What digit is it? If this 0.9 value is, you know, a few layers deep, it's going to have all these like weights coming out of it. And we're like, okay, 0.9 is great. We know from the training data that this image that's a 1 is actually supposed to be a 1. We as humans have gone in and been like, that was supposed to be a 1. So we know that this guy was off by 1 minus 0.9. We know this guy was off by 0.2 minus 0, because this should be 0. This isn't a 0, so this should not be predicting 0.2. And the best case scenario predicts a flat 0. So that's the cost function of like how far off each of these neurons were. And if this one was off just a little bit in the positive direction, like this one should have been more positive for this value, then you take the connections that influenced it the most. Like say this connection was 1, this connection was 0, this connection was 0.9, and you shift them in the direction that you want them to go. So you're like, okay, this should have been a more positive value. Let's try to crank 0.9 up. Let's try to crank 0 up by like a very small amount. And so that process happens, and this shift propagates to the previous neurons in the layer. So the previous neurons in the layer are now like, okay, I was actually off by that hop. And then they go back and they ask their, the ones that influence them to shift either up or down based on how far off they were. So this cost function propagates backwards through the network recursively for each neuron, and it asks the previous neuron, hey, influence me more in the positive direction. Influence me less in the negative direction because you're not helping. I'm getting the wrong answer. And that's what progressively happens for the data set. You plug in a 1, you run it through, you realize you were 10% off for this guy, so you shift all of the weights forward by the square root of like 10%. And the ones that were negative influence, you shift them down by the square root of 10%. And over time, the neural network finds the right weights. That was a mediocre explanation compared to like 3 blue, 1 brown, but I hope it's a vague idea of like how this kind of works. I'm not entirely sure how it works with reinforcement learning, but come to the next meeting next week and you'll find out. The very last thing is convolutions. Let me turn that back on. Oh, she's trying. All right. I can't.
All AI.
Yeah. All AI works like this. Behind it, that's why I'm giving this introduction. Like the more complex stuff that you can do of hooking up like multiple networks together, creating these intermediary steps, it's all just variations of fundamentally this. Fundamentally, it's all just neurons. It's all just neurons. Here's a lion, and that lion is being put through an image filter. This image filter is technically called a convolution. So convolutions mathematically look like this. You take a kernel, which is just a little grid that you define of some values, and you multiply it by every value in this like other, original image. And then you take the sum of all of those values together, and you spit it out right there. You see what's going on here? And over time, you just move this kernel along the image, and you get this result image. This is how a lot of filters happen. This is how Gaussian blur is done in some like bloom effects in video games where you see like a bright glow. This is how sharpening is done on your screen. This is how a lot of Photoshop filters are done. It's all just convolutions, which involves multiplying a matrix with another matrix and shifting it around the image as you do so, and taking the sum and pasting it onto a new image. So that's the original image. The output has all the edges like detected. these convolutions and the kernels can be used to extract features from the image. So you can extract really high-level features like an eye or a lollipop or a car tire or a repeating hexagon pattern as a product of a really complex kernel that you convolve the image with, and it ends up spitting out the like features that make up that image, whether it's like horizontal lines, diagonal lines, vertical lines, and then based on the positioning of those, you can convolve those and find like, oh, I'm seeing a square structure, I'm seeing a box structure, a circle on the top right corner. Yeah.
Or on a level of like,
So believe it or not, we're not actually. Oh yeah, I think behind the scenes it sort of is convolution that's going on. I'm not 100% sure on that. I think that you actually need to implement the convolutions yourself to create this effect. But no, the digit recognition thing is more just like a very raw neural network. That example that I gave, a convolutional neural network actually involves like this process of convolving the image with different kernels, and the kernels are what the model. I guess they're the weights, yeah, but I don't remember if that actually like is what I just described. I'm sorry. Long story short, you can extract these different like patterns and features from an image, and they come together to form more complex patterns. This is exactly what your optic nerve is doing right now. It's kind of cool. Like we happen to know that. It's another cool thing. Right? You see the sort of eyes, mouth, like ears, and other shapes that kind of break down into individual patterns. And it's just, you just do a lot of convolutions with the right kernels, and over time you start being able to extract features and understand what actually is existing on the image. And then you're like, oh, okay, it looks like we have a lot of horizontal lines. Oh, it looks like we have a lot of eyes in this image. Oh, it looks like we have a face because the eyes are positioned in such a way. So that's how computer vision works. I just wanted to touch on that briefly because any application that relates to images, whether it's textures or upsampling textures, upsampling images, whatever you're doing, generating new images, there's convolutions happening behind the scenes. How do you get started with AI? These are all the AI libraries right here. The big player in the game is TensorFlow, which Google is considering killing. Really, really sad. But I think there's like an open source group that's kind of trying to maintain it. There's TensorFlow 2. PyTorch is popular. Scikit-learn. Those have some built-in like neural network stuff. And again, it is this simple to generate like a neural network's topology at the very least. It's a lot more complex to set up all the data, but it's not that bad. It's really not that bad if you use one of these libraries. For my project in data structures and algorithms, I made a neural network from scratch in C++, implemented like linearly, and it's only around 1,000 lines of code. In 1,000 lines of code, you can generate a complete like neural network that you can input topologies for from scratch, and plug in like activation functions and stuff. It's not terrible. It's just not parallelized. It was a very linear thing. It was like a giant for loop, right? So it ran kind of slowly. But yeah, and now we have William. Yeah, woo. That's all for me, guys. So, thank you, William. They can only hear you. Yeah, that's probably good. As long as this blue bar is close to yellow, you're doing great.
Okay, testing.
Yeah,
Okay,
nice. You
that's
probably
good.
want this in your pocket as well, somewhere.
Okay,
Yeah.
all right. So this is the high-level overview of like how the game works. So actually, I don't have a video of how the game looks. That's probably a bad idea of my part. Let me skip to the end real quick. Okay, let's look at an example first. So you might have seen this in the show-off channel. This is not a machine learning AI, but this is an AI that's handwritten by me. And this is so we have the Unity editor here, but this is also there's also an external program written in TypeScript that's communicating with the Unity editor right now. So like the AI is not in C#, it's not in Unity at all. So there's two programs communicating. And the idea of the machine learning network is to like take inputs take the output from Unity, look at it, train an AI with it, and then take the outputs from the AI and feed it back into Unity. So it's like a feedback loop. So going back to the high-level overview, if it goes back. Yeah, that was added just for extra effect. It was just kind of funny.
Okay.
Okay, it's not going back. Oh, there we go. Okay, so back to the high-level overview. So every update, we have the Unity simulation. It goes to gathering output from the game. So like where the player is, where the enemies are, if you can use the ability or not, if you can fire, if you're reloading or not, like things like that. And then it writes to the output, which is like it writes to a pipe, which is a way to like communicate between programs on the same computer. And then we have the external AI logic. That's a TypeScript program that can be Python, that can be like a machine learning AI. And then the AI will output to the Unity, which I consider input to Unity here. And then Unity will read the input, apply the input to the game, and then run another simulation. And it goes on until the player dies. Or until like the Unity program is killed. So one of the challenges we had was how do we run like multiple instances of the same game? How do we like have 5 players playing in 5 separate worlds with only one Unity program? Because the main issue here is that you want to do it this fast and performantly. If you open like 20 separate instances of Unity, that's going to take up a lot of CPU power. So one of the ways you can do this is to like just jam 50 or 10 to 50 like games in one Unity program. So we do this by using additive scenes. We separate the physics and we separate like singletons. And that's done per game. So you can see that in the image here, we have a list of like scenes. And this is with 50 scenes open. So you can see like a lot of enemies. And the interesting thing is you can see like the players here, these are the players are the ones with the fire. And they are all separate. You can see them in the same world, but they're not in the same world. They see completely different enemies. They have completely different physics. So this is the first step. So you can have additive scenes. So you can load multiple scenes at once. That's really well known in Unity, but one of the things that people probably don't know is that you can separate the physics as well. So you can have an option that's called local physics mode, and you can set it as physics 3D. So that has a separate physics scene now. By default, if you don't include that, Unity is going to use the same physics scene as the main scene. So that's useful for most common use cases, but in this use case, you want it separate because you don't want like player in one world colliding in a different world. And you can replace physics calls with physics scene calls. So that's what the red boxes are indicating down there. That's all you need to change. So singletons are a problem in this because singletons imply there are only one of them. And when you're using a singleton for your game, that implies that you can only have one game active. So one of the challenges was that you have to remove singletons somehow. And this is an example of what a singleton looks like. So one of the things I did while designing the game and programming the game during the game jam was to make sure I only had one singleton in the entire game. So I made sure that it was easier to like move. And it's something that I recommend for any game, honestly. Like, if you can restrict yourself to one singleton maximum, because a singleton can act as a singleton for other like classes and code. So you can just like put everything you need in a game context singleton, and you're gonna be fine. And it makes it easier to switch out later, and it negates most of the downsides, which is like you can't use inheritance, you can't control the execution order, and Plus the issue of like having it being a singleton. You can't have more than one instance of a singleton. Dependency injection is something I really like to use. It's kind of complex, so I'm not going to go too in detail with it. And I see it as a way to configure your game. You can like configure like every scene. I have a game context. Every single character in the scene will use that game context to like figure out what's going on in the game. So the basic idea is that every scene has their own game context. Before you would like use a singleton, so you do game context.instance, but now dependency injection will inject it instead. So that's like just figuring your dependencies in different ways. And by doing this, every single game will know which game context belongs to them. They won't like randomly choose like the first one that they find and like accidentally share data. Just make sure that all the data is separate. So part 2 is like communicating with external programs. So typically, there's a lot of ways to like communicate with external programs. But so like for example, there's pipes, there's HTTP, there's TCP, there's UDP, and then you can also communicate with files, and there's probably a lot more that I'm missing. But the basic idea is that you have two programs that are sending inputs to each other. So this is an image of like how a Unity, like how a simple multiplayer game could work. So you have one game sending to another game. So this is a lockstep architecture. So basically, you send the input, you wait for the other player to respond. This isn't the most optimal because this isn't optimal for real-time games. If you have a turn-based game, it's perfectly fine because you are taking turns anyway. So you don't mind wait. But if you're like, if you're like doing in a real-time game with, for like example, like an FPS, if you have someone with bad internet, everyone's game will freeze for like half a second while that person like tries to reconnect and stuff. It makes it really choppy if you do this, but for like if you're communicating on a local computer, you don't like it doesn't care. The AI doesn't care that the game freezes for like 0.01 seconds. A player might care, but computers don't really care. So, ML controller is a class that I wrote, and every update it will do the top 5. External AI logic is obviously excluded because that's not part of Unity. So it acts as a controller manager class that opens scenes and makes sure that every scene has the right configuration. It also opens a pipe to communicate with the external program, and it gathers and writes output, reads and applies input to the game. And one of the big things here, one of the design decisions here was that I could honestly choose any way to do this, but like there's a lot of ways that I can go about like implementing this. But the main thing here is that I communicated with like communicated with Kyle from Data Club and made sure that he was comfortable working with like the data formats that I chose. So pipes I chose because it was simple. JSON format is a very simple, human readable data format. Like you can like binary was one of the other implementation choices I considered, but the issue of binary is that you can't read as a human. JSON, you can see like health colon 1. You can see that your health is 1. And you can see, and I'll show you an example of JSON data in a few moments. Oh, yep. So this is how the data output looks like and the data input. So here you have a player that has like a time alive, current health, max health, position, velocity, movement speed, and so on. You can also see the enemies and projectiles down here. So, for example, if the AI sees projectiles near them, they can dodge. And they can do this by saying dodge is press, true. And third direction, the aiming direction, moving direction is which direction you're moving in. So you can think of these like twin stick joysticks, so you can like move it up and down and Unity will respond to that. So applying input. So the game was designed for humans first. So now we have two ways to play a game. You can have a computer play it, or you can have a human play it. So that obviously means that you have to handle input from more than one source. So one of the ways that we did this was that we had like a triple layer input system, and so we can have a human player controller, but we can also replace that human player controller with like an AI player controller. We can also replace it with an external player controller, and those are all talking to player movements. So they'll still talk to in the same way, but they have different sources of where the input comes from. And this is the video that you just watched at the beginning. And this is, and on the right is how the code looks in like TypeScript. So this is the dodging code actually. So you want to move perpendicular to the projectile direction. So that's why you see it dodge like when it's near a projectile. Yeah, I did not worry too much about like code quality. I just wanted like this is a test AI that made sure that the API I wrote for Kyle from gAItor Club worked. Yeah, TypeScript. So Kyle is working separately from me, so he's working on his own project where he like tries to communicate with the API I wrote.
You could
Yes.
hop in.
Yeah. Yeah, so it's like any external program. So like if you really wanted to, you can have external program that relays input and output from a different computer, so you can actually network the game with that external program. It doesn't care what it's talking to at this point, because it just cares that it gets the data as expected from here. It just wants this format. It outputs that on the left, it wants this on the right. And other than that, it doesn't care who it talks to. So types are kind of like a file, but they're not exactly a file. They're just treated as a file with a file system. And you can see on here, you can use them as a string, as a stream. So I started on a pipes. Okay, that's really small. Okay. So you can have a server that acts as a pipe that acts as a server, and you can have and you can set it to in and out direction. So that means that you can read and write at the same time. So you create two streams that you can use to like read and write. So down here, so here I'm gathering data from the game. So this is enemy data and navigation. So like I have raycats that shoot in like 8 directions. So like I can see that there's a wall behind me, and I shoot a laser behind me to see if there's a wall. I shoot a laser in every single direction in the circle. And you can see like there's like a direction that I calculate. Projectiles also gather. And then here is where I like convert the data to JSON. So this will output the data that I saw earlier. And this is how the type will output. So you write a string to the stream, and then you flush, which means it writes the buffer. And then this will read line, and this will wait, because this is a blocking call, so it will wait until the program responds. If you take a look, here, this is the AI. So I have interfaces that say how the data should look, and I can access that through TypeScript. Oh, don't worry about that. Okay, so this is where the TypeScript program connects to Unity. So you see here that there's a line here that says dot pipe combat machine learning. This will connect to the pipe, and the same name is defined here. So 4 slashes is just, it's actually 2 slashes, but because of how it's an escape character basically. So backslashes are escaped by default, and you have to escape it again to get the actual character. It's the same thing, it's 1 slash at that point. Wait, so this is 2 slashes.
Slash left.
So slash, like, it's just an escape character. So slash is not interpreted as a character. So slash is interpreted as a character. Oh, I see. So I don't really know. Like, this is how Windows expects you to use this. So I assume that it points to like an absolute path on the file system somewhere. Yeah. So for any pipe that you open, you always have it here.
And like at any time I can write this code on my.
Yeah, you can open a pipe and then connect to it. Yeah.
Yes. Okay. Okay.
Okay.
I'll be happy to learn that.
Okay, so then where was I actually? Yeah, this is all public, and then yeah, and I also have links in like the respective locations for like the AI. If you want to see the ML controller, there's a link, and then I also have a bunch of links. Like this is the image. This is the article where the image came from. I haven't read this actually, but the image was pretty accurate to what I'm doing here. And you can see that there's a bunch of like links that I put. So if you want to see those, the presentation should be shared sometime soon. And I think that's about it. Okay, final slide.
Oh,
That's Kyle.
Here you go.
Thank you. Well, yeah, awesome. Thank you, William. William, look, this project was something that I said I would do, and then I didn't. I said I would try to do this in like Unreal Engine with gAItor Club, and then I realized I didn't have time. And William stepped up and has been just crazy doing this and getting it done in an awesome amount of time. It's worth noting. I'm really.
Oh, 1 slide.
Oh.
So this is the last slide here. So one of the things that I haven't implemented in the game is a custom update loop. One of the things that you with AI is that you want to speed it up, because otherwise you're just waiting a long time. Because like Michael said, you might be training this like for like 15 a few trillion generations, and you might be just trial and erroring a trillion times. You don't want to like wait in real time for the player to like die a trillion times, because that will take a long time in real life. So one of the things I could implement is a custom update loop that lets the game run at like 50 times speed, 100 times speed, and is basically as fast as a computer can handle it. Another thing that I could add is a UI that shows statistics for each simulated player. That really doesn't matter for the AI. The AI really doesn't care, but it's helpful for like humans, and it's just kind of cool to look at the player actually like play the game. And then rendering only one game mode at a time. It's also just a visual improvement. It doesn't really affect anything, but it's definitely something that's nice to have. And some takeaways are that like games can be architected in layers and as a series of steps. Games are like at the core of games. A game is just like a while loop. So it will just simulate, render, read input, and then do the same thing. And then there's also some interesting usage of Unity features and some like netcode related concepts that you can apply to like multiplayer games. Okay.
Yeah. That's really good insight. That's really good insight. The whole no, round of applause. Yeah, seriously. Like I was saying, William took over this project and did incredibly well with it. Like, we have now an API that gAItor Club can use to try to train a machine learning model, and hopefully we'll have a really cool workshop for that next week where they go into a lot of depth about reinforcement learning and the underlying like process of building a model that plays our game. Yeah. So this work was all API work, right? So it's exposing like series of pipes that can read and write inputs to the game. So we have done no AI work right now. gAItor Club is doing AI work. Don't know how they're doing. I think they're doing well. I'm hoping. That will be, it's another club on campus, so I think we're just going to merge our meetings and like collectively attend one of theirs. That today was supposed to invite a lot of them, ended up not quite working out. Not a big deal. But yeah. Did you? Yeah.
I mean, I'm just trying to understand, like the plan for the next. Is that actually that game?
Yeah.
And it's
Right.
like basically replacing text with like an actual.
That's exactly what it is. That's exactly what it is.
Actually sounds really.
So that's exactly what it is. He's going to hopefully break down this whole process of creating a reinforcement learning model in like PyTorch or TensorFlow, and hopefully it'll serve as like a really healthy introduction to AI in games because, and AI is a really generic term, machine learning in games, and an introduction to machine learning in general I think is really important to have because. Like Christ, it's coming for us all. That's why. This is no longer a JI. It's yeah. That's it today, guys. Oh, there is something else on behalf of the club. Elections are happening at some point. We put out a form. Who saw the nomination form? Did everyone see that? Cool. It would be really cool if people nominated themselves or their friends. Nominate everyone. More the merrier, because people can always be like, I don't actually want to run for president or whatever. But the entire current administrative team is stepping away eventually, and we want to transition to a new team and start teaching the new team. Like you get to work with us for like 4 or 5 months or something, and then take over the student organization until the next elections happen, which I don't know when. That will be up to that group to decide. But hopefully democratically. You're gonna have to say goodbye to Reed or William to like. We're still gonna be around here. Yeah, no, I mean we're still. So DevLUp Studios still gonna be run by Morgan. We're also going to support the Discord bot and the website. We're going to try to dramatically improve it so that it can actually like help not only UF but USF, FSU, FIT a lot more, and expand to high schools. We're going to try to register as a 501c3. Like it's a whole fun adventure, and it involves us being able to spend our time creating more long-term value rather than these admittedly really awesome PowerPoints, but they're short-term. They're short-lived. Did you want to show something? Were you pulling up GitHub? Yeah.
So to expand a bit on the ML Python side.
The camera always tracks me. That's why I just let me walk around the back, because it followed me to my seat.
Yeah, it still knows that you're there though.
It's really following me. Like,
yeah, that's all right. Oh, it found me. Just needed a wave. Okay, the camera's still on me. So this is the Python code that Kyle wrote during a voice call, and this is basically the start of the machine learning Python code. So he's doing something really similar to what I did in the TypeScript code, and this is just him testing the input and output system. So hopefully in like the next week, he'll explain how he did it, how he designed the AI, the machine learning AI, and we can see that, and we can see what it responds to like certain outputs and inputs. So the neural network will be like receiving outputs from this data here. So one of the things that Michael said is like the inputs have to be like from 0 to 1, and we can do that by like dividing like the velocity by movement speed or health by max health, and like is reloading can be a 0-1 value, and then the machine learning neural network will be outputting a value something like this. So we can like change a 0-1 value to a X value, we can change it to a button press and stuff like that. Okay.
Yeah. So, and that responsibility falls on the machine learning program because, like, you know, Williams API, the responsibility is to give the most useful data possible, and then we can, you know, train an AI to try to play it. The AI might not even be able to rely on all of that data comfortably. Maybe that's like too much data to need to play the game. It might even be able to play the game just off of the like raycasts and like the closest enemy or something, you know. So, and that's almost like a challenge that you can give yourself. Some people make AIs that play games by tracking the input data. We could have made an AI that used convolutions and looked at what was going on the screen and tried to understand what was going on. That would have required a massive amount of computational power. So since we don't have a massive data center at our disposal, we chose not to. But, you know, there's a lot of ways you can challenge yourself to make the AI act more human by actually looking at the screen and trying to figure out what's going on rather than being given a beautiful clean data set of what's going on. Yeah, that's it, guys. That's it. I might hang around and play that evolution game where you can like see the muscles and the bones, but I would understand if people want to hang out. I think that's it for today.
Like run without like
A display
without rendering.
endlessly. Yes. Yep. That was our first.
Dashback. Use dashback.
You can use dash and patch mode. Says. Really.
Like, wouldn't that just make like
Yes.
A lot faster.
Thousands of times, millions of times faster.
30 FPS though, because the game doesn't have a custom update loop, and to make it run actually faster, like it can be running 1,000 frames per second, but the game is still like moving in like real like normal speed. So I have to like multiply all the time scales by like 1,000 times to have it actually work. Yeah.
And I was like,
We don't actually. So that's a big reason why the server build, like the render, the build that doesn't render, runs so much faster. It can run at 1,000 frames per second compared to like hundreds of frames per second. Yeah.
It is worth noting that the most computationally intensive process of an AI is backpropagation. That algorithm we talked about earlier, it recursively adjusts the weights at every layer for every output neuron, is really intense. And that only happens during training. So remember, there's two stages to an AI. There's the training stage, where you make it play a bunch of games, you reward it, you give it a cost function, whatever. But while the AI is actually like playing the game, you might not be doing training. You might just be querying the neural network, which means to query it means to give it inputs and see what it spits out. Do I move up, right? Do I shoot, dodge, whatever? So that querying process, way lighter. way, way, way lighter. Like when your phone does machine learning locally to figure out what you just told it to dictate, it's only querying a pre-trained model. It is not training a model. There's no back propagation going on. And so likewise, in this system, we can run the game headlessly and simulate like 50 scenes additively loaded onto each other and be able to train 50 instances of gameplay at the same time. But when we actually want to watch the game play itself, we can just run it with the AI model and simulate one cable and actually look at it. We can simulate 50 cables at the same time, and it'll probably run just fine because we're querying the neural network. We're not performing training on it.
Like programming one or.
I wouldn't know. Pac-Man, okay.
And
Great name to play a Pac-Man game.
I'm noticing some similarities here. How you run multiple instances, basically like several input outputs.
I never took that class. I don't know. But did you? No, no. But, okay. Yeah.
Yes, and about that, okay. Also, what I did for my project was I ended up creating a function that actually calls 3 different, and then literally takes like the 4 directions and then assigns values to them, and then whatever value was the highest, it picks that direction. I'm wondering, is that sort of similar to like the
No. It's not really picking the. I mean, if the so for the XY direction of like the outputs, right? Like you would have probably one neuron that's going to output a value between like -1 and 1. Really, it might output a value between 0 and 1, and then you just subtract 0.5 multiplied by 2. But you would have like one neuron for X, one neuron for Y. There's no like pick the biggest neuron. But for the classifier, the classifier was classifying if it was a 1, if it was a 2 that I just drew. All those neurons are going to spit out what they think it is. So then, and in that case, you pick the highest.
Because it's either up, down, left, right. One of those, and whatever was the highest.
Yeah, but well, that's the thing. That's in a game where you can only move in one direction. Yes. Yes. So Pac-Man, yes. Pac-Man, yes. But there, no, because in that game you can move diagonally, and so it's really 2 values: how much X and how much Y. There's no pick highest. Depends on the application, but it has nothing to do with the implementation of the neural network. Mostly, like other than how you structure your output layer, it has more to do with like what you do with the outputs of the neural network. So in the classifier example, I would pick the maximum neuron and be like, okay, it's a 1, oh, it's a 9, it's a 5. Not so much with the movement, if that explains. Yeah, Jonas? Decision trees, yeah. So Jonas brought up behavior trees, and behavior trees, yeah, yep. Behavior trees are great. Not exactly machine learning in any way, though. But maybe if you made a machine learning model that adjusted the that used the behavior tree to play the game, and then the outputs of the machine learning model was the weights on those different arrows that decide like probabilistically what state we're going to go into next. That could be a machine learning model.
You could design sort of that's sort of what it where it just looks at like different things in the it and then the output is like it weighing like which direction it thinks.
Yeah, there's a lot of ways to like design AI. So this presentation focused more like on machine learning AIs, but there's a lot of like ways to tackle AI in games. So one of the yours sounds like you're like assigning like weights. Like that's actually a very common like strategy. So you can like weight different actions in the game to like decide what to do in the game. So like for example, if you're like doing an RTS game, you might have the AI be weighted hand weighted to build new buildings, build armies. And that's fine-tuned by hand. And that's kind of like a neural network, but like the main point of a neural network is to have the AI figure out what's most optimal by itself, not have a human fine-tune it.
Well, you said earlier, like these are like machine learning AI. Are you implying that there are some AI that don't use neural network?
Most AI. Most AI, right? I mean, like a decision tree is not, the type scripting that he did, which is a if-else statement and like a random choice, pretty random. If you look at like most game behavior, if you're playing like a stealth game like Hitman or something, the AI is constantly running this loop that's like, oh, I last saw the character here. My state is now aggro. Let me go and patrol random points in the area where the player last was. And then they walk over there and they walk in circles for a few minutes, and then their state goes back to idle, and they go back to their default waypoint and walk a cycle. That's not much.
It's like a lot simpler.
It's not just simpler. It's not dependent on machine learning whatsoever. There's no
Different technique.
That's a good. I like that word. Yeah, deterministic. So like programmatic, algorithmic, very like linear in its process. Machine learning model takes in a lot of variables and over time tries to predict the optimal way to play the game, but it's like very fundamentally different, right? Like we're talking the difference between if-else statements and like effectively 3,000-4,000 lines of code and a massive data set in this completely different process. Is that clear to you? When would be better? Okay, so that's a good question. So it's how much control you want over the AI is saying. Asymmetric gameplay, you might want a deterministic enemy AI. I'm just trying to dictate for our viewers on the stream. So what he just explains that a very complex game would require AI most likely. Even simple games, like it can be used to optimize something in a simple game. I think the trade-off really, like at the end of the day, AI almost always wins. At the end of the day, if you give it enough data and enough compute time, it'll always do its job better than like anything you can come up with, or equally. So like in a game like tic-tac-toe, very deterministic strategy, right? Like you can program the AI decisions for tic-tac-toe. It didn't follow you. You're good. Yeah, it's just supposed to pick a random person and track them. Tic-tac-toe. If you tried to do a machine learning model for tic-tac-toe, you totally could, right? Because you know at every step what the next step should be. So you have a perfect set of training data. Like you are guaranteed, whenever this pattern shows up on the tic-tac-toe board, you better play there next. And if you play anywhere else, it's not going to be good. So the AI will very quickly converge. That's a big vocabulary word in machine learning. It will converge on the right solution very quickly because you have perfect training data, you have a perfect output. So very soon, that AI is going to be predicting an output that is directly equivalent, almost perfectly equivalent to the like one-to-one, writing an if-else statement, like creating a simple little AI to play tic-tac-toe perfectly. But you as a human have the brain power to know how to play tic-tac-toe perfectly. You don't need to waste your time writing an AI. So it's a trade-off of time and compute and all this like added complexity. Writing an AI is no easy task. I did show that it was 4 lines of code there, but you have to create a whole API, you have to generate all this training data. Like, it's a grind for a bigger game. So when people are deciding to apply machine learning models to these really big titles, it's, you know, they're weighing a really heavy decision there. That's like months of effort and lots of software engineers being paid to work on that. It's a trade-off of resources, I'd say, more than anything. Like, you can use machine learning to play tic-tac-toe, and you can use a comical decision tree to play Madden animations, or Assassin's Creed Unity. If you were here for the animation workshop, you heard me say they had 13,000 animations in a giant state machine. Disgusting, hilarious, right? They had manually created a massive state machine with like 4,000 different player animations to choose from. With a state machine, it's one of those like decision trees. It's a if-else statements, more or less. They could have done that with an AI, and now The Last of Us 2 decided for our animations, instead of using a state machine, we're going to pick the best animation based on a machine learning model. I hope this sort of gives you an idea of like when you apply.
I can see. It's impractical.
Yeah.
Manually.
But it is practical for like chess. Chess seems like a simple game, but there's no perfect set of rules to play chess because it's like there's a whole tree of possible moves that you can make. And so the most basic manual algorithms are like Monte Carlo tree search, where it just generates for every move, every possible outcome, and it simulates it to a depth of like 5 or 7 or something. And then humans write heuristics that are like, oh, if we manage to swallow 3 pawns and a queen, I weigh that at a 9 out of 10 heuristic score. So I'm going to go with that move set from the 3,000 moves I just checked. A machine learning model takes the move sets and knows, because it played a trillion games, that move set is better. It doesn't have human-made heuristics that compute the best score for the move set. It uses machine learning. And as a result, machine learning models play chess better. Yeah, both work. A machine learning model is, in fact, a little more efficient. It's harder to train, so you have to play a trillion games, but it's more efficient than a Monte Carlo tree search that does things automatically, because a Monte Carlo tree search has to explore every possible solution, whereas an AI can make like, it can check the first layer of solutions, be like, I like where this one is going, and then branch out only from that one and really prune the tree of decisions it wants to take on and explore the game deeper. Like, AI has the potential to run even faster than a human-written like heuristic algorithm. But the training of an AI will always be more computationally intensive than the effort that it took like a guy to create a few heuristics for swallowing up pawns and queens. Did you want to add something? You totally did.
That's the question. So I'm wondering, question. Machine learning,
Planning and so William asked how machine learning deals with planning and strategy. So we're talking like an RTS game like StarCraft.
things that machine learning struggles
So William explained that machine learning. He's heard that machine learning struggles with long-term planning and can only pick up patterns based on the current state of the game, and that depends a lot on how it's just how you implement it. Like, sky's the limit with these things, but if you create a deep enough neural network that is also given enough inputs that include like the prior states of the game, it can probably plan into the future. I'll tell you this, I read the article on the Planetary Annihilation AI, the one that plays that RTS game that I showed on screen earlier, and I know that the neural network for that, all it does is it combines the collective data that it knows about its enemy, and it doesn't make low-level decisions of where to place buildings. It makes high-level decisions of what ratio of units to produce and how big of a group to send to different enemy hotspots, and then how to time that. That's the decisions that it makes. And then the rest is like manually programmed. So it's a combination of AI and human decision making, because the AI would be a little too chaotic for deciding where to place buildings on this like big map. At long-term planning, I know this, StarCraft remains unbeaten. AI, I don't think is good at beating players yet. The only thing that it's good at beating them is a symmetric Protoss versus Protoss map. That's the only case that an AI can win at for some reason. And I think it has to do with like, well, there's this concept of like overfitting, right? So in statistics, if you overfit a model, whether that's like even simple linear regression, like drawing the mean line on a scatter plot, you can overfit a model. So you can use like a, I don't know, quintic regression on a scatter plot where, does that, hold on, wait, does anyone, do people kind of intuitively know what overfitting means? Yes, no, maybe. Here's a scatter plot. Here's some data points that look like a line, right? We can use linear regression to plot the like linear thing and figure out, okay, yeah, it's just a line. If we wanted to, we could screw around and use like regression or something, and we would get like that. And it's like, wait, this fits the points better, probably. It probably reduces the mean square error of like how far all the points are from the line, but it doesn't accurately depict the data at the ends. You know, the data doesn't go off to infinity, it continues linearly. So overfitting results in poor conclusions about things outside of the like problem domain. And it also results in like not correct behavior. So if you have like an AI that you've trained on nothing but Protoss versus Protoss gameplay, it gets really good at Protoss versus Protoss gameplay, but it doesn't know how to play StarCraft. It just knows the best set of decisions to make in like a series of steps against Protoss players. And you also let the AI cheat usually. You might give it like an actions per minute in a strategy game of like, oh, you know, the AI can place 8,000 buildings in a single click. Whereas like the poor like human player over there is, have you guys seen that Korean guy playing with his foot at the end of the match on StarCraft? Oh God. So yeah. It's but even if you don't let the AI cheat, I'm not sure that I'm not sure. I don't know how to like. I'm doing my best to give you like the relevant information on AI and long-term planning and strategy. It's pretty bad at predicting things well into the future if it doesn't have like memory of that. It really depends on the AI's implementation. So in a StarCraft round, there's a very like, you can probably organize the round like just as a human thinking about how to best play StarCraft. There's the opening, which is like the set of moves you make in like the very first few seconds. In those first few seconds, you have no data on your opponent. There's an optimal opening strategy that's been accepted by like humans in StarCraft. It's like, all right, place pylons here, allocate like 5 out of 10 workers, 2 out of 10 build a base on the nearest thing, whatever. Like, if the AI plays enough games, it's going to learn that pattern. And it's perfectly overfitted to that pattern. You could say it's overfitted because it will never like adapt to another strategy at that point. But that's a win. That's great. Like that's the best pattern possible. It's like playing tic-tac-toe with an AI. It figures out the best pattern. But then as things become less deterministic later in the match because the enemy makes like certain clever decisions and the AI sees like new data, it might not know how to respond. But what it might know, if it was designed in such a way, it might be given the delta time since the start of the match. So maybe the AI, after like 3 trillion rounds, realizes that sometime between minute 5 and 10, minute like 7.5 and 8, is exactly when it needs to like send out its first raiding party, send out its first like, I don't know, defense line and put it like right there. And so you end up with an overfitted model that knows how to play based on time really well. And so because it has that like time dependency, the AI becomes almost, like if you gave an AI nothing but time as an input, it eventually just becomes, it encodes a signal, a function of time. Like at the end of the day, the AI just becomes a giant like waveform of what it's going to do over time, where that waveform describes like the different outputs. So you're going to end up with something overfitted to time. Hopefully it responds to a combination of time and different patterns. and it learns that like later in the game we're doing this, earlier in the game we're doing this. And if you give it inputs like what it's seen the enemy do, maybe it, you know, learns to multiply time and the weights of time by those inputs to be like, okay, we saw enemy fighter jets in the first 45 seconds instead of the first 30 seconds, therefore the game is moving slower, therefore I will make these decisions. And, you know, it doesn't explicitly do that, it does that implicitly by multiplying these weights and figuring it out over time. So, I don't know, that's sort of, so I'm, that's good, okay, cool, yeah, geez, man. In fact, want to see an AI that encodes for time? Evolve. It has. Check it out. Evolution. Runs in WebGL. It's extremely cool. It's really cool. So let's do a joint. Bam, bam, bam. Bam. We'll do some bones. And we can do some muscles. And these muscles will either expand or contract based on what the neural network tells them. What does the neural network see? Nothing but time. Nothing but time. In fact, let's go look at the neural networks. This is the first generation. There's two of them being simulated at the same time. In Williams' example, yeah, they don't know what they're doing. In Williams' example, we simulate like 50 additive scenes. Here you're seeing like 10 additive scenes. They're all playing the game together, they're not interacting with each other, and we constantly see the best one highlighted and the others have their opacity decreased. Pretty good way to display like a lot of additive things. Let me show you what the neural network looks like. There's the neural network. It's, look at that, time, 10 neurons, will the muscle flex. That's it, that's the neural network. How about we give it some more layers? Great, now we have 3 intermediate layers. No, this will allow it to make much more complex decisions. So if there's only a single line of neurons and it's adding them up together, the output is going to be nothing but like, and in fact, time is probably not what's going in. It's probably like time modulo 100 or something, like the first 100 values of time, because it probably repeats. But this neural network over time, like the more neurons you give it, the more precise of a signal it's going to encode for flex over time. That's all it is. If you give it very few neurons, it's going to probably look like a sine wave of flex over time that gets adjusted. Let's try that. If I give it nothing but 3 layers, and I give it like 3 neurons. Look at that, absolute jellyfish. And go back. Yeah, there's this. It's just gonna. Yeah, it's a little dumb. Let me turn on hardware acceleration. We're definitely playing this on the CPU. Oh, the administrator disables hardware acceleration. Man. So. Yeah, they're all like twitching at like really high frequencies. They haven't figured out yet how to stop twitching. but they figure it out. They figure it out eventually. We'll see some wiggling eventually, hopefully. But maybe it's just like too stupid to ever figure out how to wiggle. Maybe 3 neurons encodes nothing but a gradual expansion over time of the muscles, or a contraction. It's trying to get as far as possible. And eventually the terrain goes and does different things. There's like a mountain terrain, there's like gaps. There's a lot of web games like this. This isn't the first one. There's one that generates cars, and the cars like race. But instead of AI, it's just generating the structure of the cars. So it's randomly placing wheels and bones, and then it's mutating them and using a genetic algorithm to mutate them. This is not mutating the structure, it's mutating the neural network based on the reward function of like which of these like 10 that are being simulated did the best. And then it takes like the top 2 or 3 and it breeds them together. So it takes their weights, averages them, and like randomizes some offsets. Hopefully we'll start to see some jiggling soon. We gave a jellyfish a lobotomy. Like this is pretty bad. Yeah. Well, if here, let me here. We can. No. it's very unfortunate that we can't like if I do like 4 seconds per generation, hopefully we'll see some oh, we can do jumping. Like how high can it jump? That's pretty cool as well. We can also give it some I'll give it another joint right here. And we'll give it a muscle right there. And then finally I will go to the brain and I will do and 4 neurons. There you go. 4 layers. All right. That should be cool. Simulate in batches. Why not? Oh, this guy. You see him twitch there? Oh. Wait, that looks kind of sus. Hold on. Oh yeah. Oh yeah. So, and all these things, right? It's like encoded contractions over time.
It's going.
Oh man, it stops for some reason. So yeah, this is pretty good. This is pretty good. We can watch this evolve over time. It's a pretty healthy introduction to like machine learning.
Yeah.
I know that we want good, but it lasts more.
Codeball doesn't. I don't feel it goes into enough depth. I think 3 Blue 1 Brown's a really good place to start. The coding train. You heard of the coding train? It's this like MIT professor has like very interesting graphics. But that's a good one as well.
Like,
Mm-hmm.
like I use Codeboard as a one.
As a 202 class. Yeah. Oh, of course. No, I don't think UF classes do a good job in English, especially in math. Not a fan of how they teach math here. But
this is a 3. It's sloppily written and rendered. It's just that you come away feeling like the structure itself is motivated. And it feels like
Yeah, well, that's after.
too bad. Good answer. The calculus for like AI and actually reading the notation for it has it tends to have like a lot of partial derivatives and partial differential equations, but you don't like partial derivatives aren't hard to understand. They're not hard at all. They refer to like gradients. So calculus 3. If you understand calculus 3 pretty well and like maybe a tiny bit of diffEQ, you're fine, I think. Calculus? No. Calculus 3 is like vector math. It's not bad, man. We're part of calculus. We're part of calculus. It's okay if you struggle with calculus, but like, what? I think you probably had like a garbage professor. Calculus, like everyone that's ever struggled with math just had really bad professors, in my humble opinion. I bet you would be fine with like some better training. If you want, there's this really shredded guy. He's kind of distracting. His name is Professor Leonard. Professor Leonard, this guy right here, oh man, this guy teaches calculus better than like anyone on the planet. Go, this guy, he's shredded. He's shredded out of his mind, and he covers like all sorts of calc. Look how confident he is. What an absolute lecture. What a lecture. Like he's massive. He's massive. And he covers everything. He covers proofs, linear algebra, calculus, and his calculus lectures are better than like anything on the internet. Like anything. If you want to retake calc, just watch like some of his videos, binge watch them. He's so good. Oh my God, he's so good. He's so good. Like this guy, I took calculus 2 in a week and a half watching this guy, and I just took the test. Like I procrastinated, and I just took the exam. I'm serious. I took all of Calculus 2 in a week and a half with this guy's videos and a little bit of added content, but mostly this guy's videos kind of carried.
It's not hard to do. It's really nice to do. Is take this sequence from percent y that's one. That's very good. It's absolutely.
This is really like I think we should all aspire to be like this guy. I'm not even gonna lie. Like great lecturer, charismatic, and takes care of himself very good.
That's cool.
It looks like Henry Cavill. There's a reason why he has like Superman as his logo.
This is
Like he has a Superman shirt. That's his profile picture. It's him.
Hi, I'm Professor. Hi, I'm Professor Lerner. I'd like to welcome you to my math.
Data science related courses are really good. There's a class here called Machine Learning for Computer Graphics, and it's like terrible. It has one of the lowest rate my professors' ratings. But I'll be honest with you, the worst professors make you learn the most because they're just so catastrophically bad that you have to like carry yourself not to fail. No, I'm serious. Like I have taken like no, it actually has like what? There's no textbook. No, I don't. I think it's this. Her name is, I think like Teresa Schultz, Mother Teresa, and she's not as philanthropic exactly. She gives like terrible instructions, but it makes you just research everything, and it's like I didn't take the class personally. I've heard stories from my friends, and I watched them like do the machine learning stuff for the class, and you're like writing convolutional neural networks, and you're doing all sorts of machine learning on like image data sets that you're provided, and it's really difficult. And you end up learning a lot. Just diving deep into this stuff on your own will always be better than anything college can do for you. College can organize the content. It can organize it, but I don't think there's any lecturer that will ever beat the collective quality of the internet. I think we live in a society where like the time of the lecture has passed. Now it's the job of universities to organize data so that we know what order to best learn it in. But that's just my philosophy. Yeah. No, I'm okay with the stream continuing to run. I think this is kind of fun. Like, people are going to have a lot to reflect on. Hey, Generation 17. It's still, it hasn't figured out how to like keep jiggling. It just gives up. Okay.
Break the computer.
Say less. I'm gonna make this computer. Oh man, it's already on 100 CPU. I'm gonna make this computer disappear. Oh, it's doing pretty well. Oh, no, it's because I set it to simulate in batches of 10. So it's doing the first generation, step 1 of 10. So it's doing 10 batches of 10. In fact, let me go uncheck this. There we go. Yeah. No, this will give us results a lot faster, you know? I'm gonna end the stream now. I think we're done with it. I mean, we've learned everything we can about machine learning. We're basically experts. Like,